So here we're looking at topics 3.2 to 3.6. Again, things that I took note of, just looking through practice problems, but I in the book didn't focus on. Things that you might have got from reading the book or listening to, other things I taught, but these are just miscellaneous things that I noticed in practice problems that I think are good to highlight. Okay, so 3.2, something that would be good to highlight is to be comfortable with identifying what type of solid is represented, because there's a decent chance, not change, chance you might get a question like that, where it gives you a picture of a solid and it asks you to identify what type of solid it is. So refer back to types of solids Bogle. If when you're doing the practice problems you get any of these wrong or you're not sure or it doesn't look familiar, that would be my first recommendation to you, that you look back at this Bogle on types of solids. After that, then I would just take these notes. If you're still not clear, I would say a couple things. First of all, ionic solids have opposite atoms, atoms of opposite charge, right, surrounding each other. Molecular solids, I would note that there will probably be dotted lines in the structure. Those dotted lines are probably going to indicate some sort of intermolecular force, such as hydrogen bonding, occurring within the molecular solid. So there should be some sort of distinction between the covalent bonds and the intermolecular forces. Network covalent is also going to be similar to molecular solids. We're going to have nonmetals in covalent bonds, but in a network covalent solid, there's only covalent bonds. So there shouldn't be any dotted lines or anything like that. As we can see in the third row here, comparing the third row to the second row, in the second row, we have those dotted lines indicating intermolecular forces. And in the third row, there are none of that because it's all covalent bonds. Then in metallic, you could see all of the same atoms, such as in this, sorry, I'm moving the mouse on the screen. So the third row, right, as you can see there, there's all covalent bonds. Second row, we have dashed lines, like here, which are again representing the molecular solid, so the intermolecular forces versus the covalent bonds. Then if we're looking at the molecular solid, well, we can see, for example, here, they're all the same atom, which is not going to happen in the other types. Or here with brass, copper, and zinc, it's kind of helter-skelter. It's not the same atom, but it's not like the ionic structures up here, where it's opposite, where it's always alternating one and the other. And it's not covalent bonds like in the molecular solids having the covalent bonds and intermolecular forces, or in the network covalent solids just having the covalent bonds. It's different than either of those. It's helter-skelter, which is not a super sciencey word, but that's how I would describe it. So those are kind of my little tips for if you're struggling to identify types of solids. But I would first again look at the Bogle. Okay, let's talk about 3.3. What things from 3.3, just looking at practice problems, I think are important to keep in mind or things to know. So I would say know that enthalpy of vaporization is always greater than enthalpy of fusion. In other words, the energy to cause something to become a gas from a liquid is always greater than the energy it will take to go from a solid to a liquid. So liquid to gas will always take more energy. And we can justify this or explain this by thinking about that the gas phase completely separates the particles and what holds them together. So comparing a solid to a liquid, for example, water, yes, there's energy that's required to take the solid and turn it into liquid form, but the molecules are not completely separated from each other. they still have the attractions of the intermolecular forces holding them together in liquid form. The density of liquid water compared to solid water is, I believe, like 4% greater. Whereas, if we're looking at a gas, it's taking up way, way, way more space. Therefore, those intermolecular forces between the water molecules in the case of turning into a gas are completely overcome. And so that takes more energy. So again, the takeaway is that the enthalpy of vaporization turning into a gas is always greater than the enthalpy of fusion. That's the only thing that really stuck out to me from 3.4. I mean 3.3. 3.4, looking at Pivner. So AP Chem, justifiably, wants to make sure you can think about this formula in a conceptual way, such as amount of relative change, instead of just plug and chug. Here is an example of what I mean. This does not require using PivNert and writing it down and putting the numbers into your calculator. It doesn't, okay? You can, for some of these problems, and that's part of the speed thing too, you need to be able to do these problems without your calculator, with just using your brain, because of the time factor on the exam. You only have so much time. So some of these questions, if it's a PivNert problem, right, and student Alice, let's say, student Alice solves it in 10 seconds, and student B, Bobby, solves it in 3 minutes. Student A, Alice, is ahead. She has effectively gained a minute and 10 seconds or so on her exam for other questions. Student Bobby has lost effectively a minute and a half for other questions. Let's say there's 5 questions like that on the exam. There's probably more, but let's just say 5 questions that have to do with conceptual knowledge like this, where you could or couldn't use a calculator, but you're not intended to, and some students do. Well, then student Alice has gained 8 minutes to look at other problems that are a little more difficult and finish. Student Bobby has lost that same amount of time, if not even more, effectively, right? So it's really important to be able to think about these things conceptually. So a rubber bladder used in deep sea research is brought from the ocean floor to the surface. Ooh, fancy, going all the way down there. During the trip, the temperature of the gas inside increases from 330 Kelvin to 280, while the surrounding water pressure decreases from 3 to 1 atm. Now you might think, oh, plug it in, No, you don't need to do that, because think about it. 330 Kelvin to 280. I don't know what percent change that is, but it's not more than 30% for sure, right? Whereas 3 atm to 1 atm, 3 times 1 is 3, okay? This is a bigger change mathematically. I don't know how to explain that better than to say it's a bigger change, okay? Ask your math teacher about how to explain proportionality in a very, high school math technical kind of way. But this is a bigger change. So what does that tell us? Well, if the pressure is a bigger change, then that's going to be a bigger factor than any change in temperature, regardless of the direction temperature is heading. So in this case, the pressure is going way, way down. Well, looking at Pivner, if the pressure is going way, way down, then to compensate, if everything else remains relatively the same, volume must increase. And so the answer here is that there's an increase in volume. Okay? So that's how you can think about some of these conceptually. Make sure you actually have to use your calculator before you actually do, if that makes sense. And that's why, again, I have you do a bunch of practice problems. Because the more practice problems we do, then you can recognize these trends and identify them in real time a lot easier. so you can do these problems. Okay, adding gases together. When 2 liters of helium, 6 liters of nitrogen, and 4 liters of argon, all at 20 Celsius and 1 atm, are pumped into an evacuated rigid container, the final pressure of the container at 20 degrees Celsius is what? So this is, I noticed several of these in the practice problems, and to me they're kind of weird.
Sorry to interrupt class, teacher, but students just want you to be aware there is no leave button today. No leave button today.
I don't know if you heard that, but I'm recording myself and they just made an announcement. I don't know if you could hear the announcement. So I saw several of these types of problems where there's different gases in certain size containers being added together. It's kind of weird. It's kind of niche, but there's a quick way to solve this. So I want you to go ahead, pause this video, and think about how you would solve it, figure it out, figure out what the correct answer is, and then I'll show you the way that I like to do it after seeing a bunch of them that I think is fairly quick. Okay, so hopefully you've paused the video and have solved it and given your answer. Okay, so this is my reasoning. So we take the formula PV over T equals PV over T, but the temperature is constant, right? Because all the temperatures are the same, so we eliminate that. So we know that as pressure goes up, volume must go down. As volume goes up, pressure goes down, and it's proportional. So if volume increases, because we're taking gases in smaller containers and putting them in bigger containers, then pressure, I should say pressure, decreases proportionally. If volume increases, pressure must decrease proportionally. So to account for this, look at how I just did the math. I take, and in this case, I didn't even have to include the times 1 because they're all times 1. So even if I didn't do that, it would have been the same. But this would account for if some of the gases were at different pressures than other gases. And I can't remember if I saw any AP Chem problems that did that or not, but I feel it's probably better to put that in there just to be safe. But the original gas had 2 liters. Okay, it's going into a 6-liter container. Well, its pressure will now be 1/3 of what it was because the volume went up by 3 times, right? So 2 over the original volume over new volume times the original pressure. And then I do that for every gas. So in this one, the pressure will be the same because the volume of the container hasn't changed in the second example. And then the third one, it will be 2/3 as what it was, right? And you could have something where the original container was, let's say, was 8 liters and the new container's 1 liter. Well, then, of course, the pressure will go up and you would still account for that. But no matter what the change is, you can do the old over the new to account for how the pressure of the gas will be changing when putting in the new container. You add those all together and it gives you the answer quite quickly. So this is, I think, a method to solve these putting gases together kind of problems pretty quickly. If you had another method that you just did, that you got the answer quickly and worked for you, that's great. But if the container gets bigger, just again conceptually addressing what's happening here, then the pressure will decrease proportionally. And so that's all I'm indicating here. Basically, this is a ratio showing the relative change in volume, and that'll be multiplied by what the pressure of each gas was to determine how much pressure that gas is contributing to the new container effectively. Another thing, again, I don't know if you will see something like this or not, but in some of the practice problems, they talked about pistons. I don't remember the book talking about pistons. I don't see pistons in the standards, but it doesn't say you can't talk about pistons anywhere. So maybe you can. Well, a piston, and this is also where like, there's some people who know way more about, I don't know very much about pistons, like cars and such, not really something I know about. So anyone with a civil engineering or mechanical engineering background, like a bunch of my friends, is going to know way, way more about this than me, okay? But this is a definition we can work with and a description we can work with just for AP Chem. we have some sort of cylinder, and then there's a movable disc. So we can imagine that there's pressure on this side that's pushing in on the disc. There's pressure pushing in on the disc. And so the pressure of the gas inside is going to be constant. So if the temperature goes up, the gas will take up more space, pushing the cylinder out this way. If the temperature goes down, then the gas will take up less space, pushing the cylinder or allowing the cylinder to squeeze more, because there's a pressure coming from this side that's going to stay the same. So the pressure inside the cylinder must stay the same. That's my very basic understanding here. Like, somebody with a civil or mechanical engineering background is gonna, might laugh and say that's not good. Actually, if one of your parents is, I'd actually could talk about this with them. Actually, I probably should just reach out to one of my many engineering friends. But let's look at this in action. So again, I'll teach here that as the volume changes, keeping temperature and pressure constant, pressure stays the same due to a movable piston. I think the bottom line here is that pressure stays the same. So if the volume's changing, for example, if they're asking about a change in volume, then the temp and the pressure are going to remain the same, for example. Okay? Let me say that again. If the question's asking about a change in volume, we're going to assume, man, 2 rings and an announcement in this video. We're going to assume the temperature and the pressure remain the same. So as I was saying, the pressure is always remaining the same. So the pressure is not changing because this piston is pushing down on the gas. And so the volume will change, but the pressure inside the cylinder will not. At least that's what I've seen in the AP Chem problems that I've saw that address pistons either in MCQ or FRQ. So let's look at an example. And I think also the practice problems dealing with this might help you. So a student investigates gas behavior using a cylindrical container fitted with a frictionless, movable piston of negligible mass. The cylinder initially contains 0.4 moles of krypton. The student next cools the gas with the piston free to move from 310 to 260, and the measured volume of the gas decreases. Using principles of the kinetic molecular theory, explain why the volume of the gas decreases when the temperature is reduced. So go ahead again, pause this video and try to answer this question, and then I'll give you my answer. Okay, so hopefully you pause the video. Now, as I said, hopefully I've been clear enough that we're going to assume with the pistons that the pressure always remains the same. Okay? So we're assuming the pressure remains the same. And in this case, the temperature is decreasing. So what will happen to the volume for the pressure to remain the same? Well, let me write it out. If the temperature is reduced, then the molecules hit the sides of the container less. Or less rapidly. So, for the pressure to remain constant, could you please shut the door, please? And then the link's on Google Classroom. For the pressure to remain constant, that means the size which is the volume of the space, is reduced. Okay? So again, think about this in terms of Pivner. We know the pressure remains the same, and the temperature went down. So for the pressure to remain the same in this situation, this side of the equation went down, right? So we know that something on the pressure volume side must go down. Pressure remains the same, so volume has decreased. But we can also conceptually explain this. If the temperature goes down, then the molecules are moving less. If they're moving less, they're hitting the sides of the container less. If they're hitting the sides of the container less, then there's less collisions with the sides of the piston. The piston keeps constant pressure. So the piston is going to move inwards, decreasing the amount of space available for the gas, which in turn actually keeps the pressure constant, because as we said in the piston, the pressure remains the same. So when the space decreases, because of the decrease in temperature, the pressure actually gets maintained and the volume decreases. So I think that's the most common thing I'm explaining in this miscellaneous, but let's look at 3.5. So miscellaneous things from 3.5. First of all, just remember what temperature means. Temperature is a measure of random kinetic energy, so don't forget that. And another thing that they like to assess in these questions that's kind of physics related, and this is in your AP Chem formula sheet, kinetic energy equals half times the mass times the speed or the velocity squared. So this is really a physics idea. But what does this mean? This means that if the mass of something's big, then its velocity is smaller relative to the amount of kinetic energy it has. So the application here is that two gases at the same temperature both have the same average random kinetic energy, but they don't have the same speed because they have different masses. So at the same temperature, the smaller particles will have a greater average speed because they have the same amount of average kinetic energy, but they're smaller. So with the same amount of kinetic energy, they move faster. Same thing, if you take a dumbbell and a little ball and you throw them with the same amount of energy, give them the same amount of kinetic energy, which is going to move faster? The little ball, duh, right? The dumbbell's not going to get very far, no matter how, even if you're Arnold Schwarzenegger 2.0. It's just not going to go very far because it has more mass. And so at the same amount of kinetic energy, the velocity will be less. So let's test your understanding. Go ahead, pause this video, pause this, look at these possible answers, and then we'll see. Okay, so hopefully you answered the question. And so the correct answer here is A. So what this is telling us is helium is going to escape and move faster because it is smaller than CO2. So because it's smaller than CO2, it is at the same temperature, the gas particles are moving faster, and so they escape more quickly. Another application of this is if we're looking at a graph like this, larger mass means a slower average speed. So all these gases, as you can see here, are at the same temperature, but the larger the mass, the slower the average speed, and the more bunched up the speeds of the particles are. Now, we've already talked about this, or we'll talk about it in the Maxwell-Boltzmann distribution focal. But why I bring this up again is pay attention if a question is asking about speed or kinetic energy. Because I noticed the AP Chem questions on gases tend to assess students on if they understand the difference between speed and kinetic energy. Do they understand the difference or not? Or do they think they're one and the same? And they are not. As we just said, if you think that picking up a dumbbell and picking up a small ball is the same amount takes the same amount of energy to move them at the same speed, you are bonkers. I mean, there's something wrong with you. I'm sorry. They don't, right? Things of different mass moving at the same speeds have different kinetic energies. So, but for some reason, when it comes to this, students get that confused. So keep the difference between speed and kinetic energy clear in your mind. For example, are H2 and O2 at the same temperature here? Answer that. You should say, yes, they are. Even though they have different average molecular speeds? Yeah, because they have different masses. Where would F2 curve be drawn here? Should answer that. It should be to the left of oxygen and even steeper, right? Because it has more mass. And so there's less variation even more on the average speed, and the average speed is slower because the mass is higher. And if you're confused on that, again, keep the difference between speed and kinetic energy straight in your head and look back at that Maxwell-Boltzmann distribution POGL. Or, look up other resources too. I'm not offended when you do that, obviously. Okay. Lastly, with miscellaneous things from Unit 3, 3.2 to 3.6, we have 3.6. So things that I noticed from MCQ, FRQ, etc. questions that should be focused on in 3.6. So strategy for AP Chem non-ideal gas problems. I think in the book and in the POGL and in the recordings I made, etc., it goes a little bit deeper than even what the AP Chem problems tend to ask. Therefore, I don't want to overcomplicate it so that when there's a simpler question, you get it wrong because we've actually gone deeper into the concepts in class. So here's kind of my simplification strategy for dealing with non-ideal gas problems in the context of AP Chem MCQ. I would break it down into two things. If pressure is greater than expected, the space of molecules appreciably decreases real volume. So if the question indicates pressure is greater than expected, the answer you're going to give is that the molecules space is decreasing the real volume because the molecules are taking up space. If the thing says that the pressure is less than expected, it's the intermolecular forces of the molecules. It's either this or that, okay? So read that again, but those are the two explanations. They don't complicate it too much from what I've seen. So here's the non-ideal example. Well, it's a great non-ideal example. That's what it is. A phenomenal non-ideal example. So go ahead and read this one and answer it, and then we'll go over it. Okay, so hopefully you answered this one. And so the answer here, the explanation that the ideal gas law does not account for the molecular volume. The real volume is less than the ideal. Okay, we accounted for that. As you see in the problem, has a measured volume greater than predicted by the gas law. Okay, so why would it be taking up more space, measured volume greater than that predicted by the gas law? Well, if it was in like a closed container, I should change this explanation the way I wrote it slightly. But the real volume is less than ideal if it was a closed container, but in this case it's expanding. So it's actually, let me change the wording on here. The real volume, or the volume, is greater since the pressure is higher than predicted. Okay? So that's the reason. The volume's greater because there's more pressure than predicted. And why is that? Why is there more pressure than predicted? Because the molecules themselves take up space, which has increased the volume. So that goes back to the two reasons. There was an increase in volume. Why? Because the pressure was greater than expected. Therefore, it has to do with not accounting for the volume of the gases themselves. If there was a question saying there's a decrease in pressure, why? The pressure is less than would be ideally expected. Well, then if there's a decrease in volume because the pressure was less than ideally expected, then it has to do with intermolecular forces. So even if they're talking about volume, take it back to pressure and then the explanation. Okay, lastly, ideal conditions. Simplifying what's been said in the POGIL and the book for the same, for AP Chem MCQ at least, gases are closer to ideal behavior at higher volume, low pressure. So you could just have a very simple question saying, this gas is closest to ideal volume when? And the answer should be whatever is high volume, low pressure. Basically, the gas particles are further away from each other then, so that's why that's the answer. So look for the high volume, low pressure answer. So in this case, which of the following will CH4 be expected to behave most like an ideal gas? Out of the options, it's C, because this is high temperature, low pressure. We should also add that here, okay? So high volume, high temperature, low pressure is closest to ideal behavior. High temperature, high pressure, high temperature, low pressure, high volume. Basically the things that mean that they're moving more and there's less of them. So low pressure means there's less gas. And if there's high temperature or high volume, it means they're taking up more space. Okay? So if there's less gas, which means low pressure, and more space, so high temperature or high volume, that's going to be more like ideal because the gases are really far away from each other. So the space they take up is not really significant, and their intermolecular forces are not significant. And so those are the conditions most ideal: high temperature, high volume, low pressure, because we want to get the gas particles as far away from each other as possible. As far away from each other as possible in order to make them most ideal. Because when they interfere with each other, they're less ideal.